Howdy, everybody. I hope wherever, whenever you are, things are going well for you. I truly wish the best to everyone. I hope you're enjoying your day and maybe we can learn a little bit today. So, I want to do something a little bit different. We've been working on the int code computer and through the advent of code. I think that's been a lot of fun. We've got like 3 or 4 more to solve, but I want to try something a little bit different. I saw a puzzle online and I thought, oh, it'd be fun to solve this programmatically, and talked about it. And it turns out, if you look at the title, an easy way to solve it is via a graph. Um, and apparently, I'm a sucker for graphs. So, but it got me excited, and I feel like at least I enjoy the videos better when I'm excited about trying to find a solution and talking to you all about it. So that's what we're going to do today. We will get back to the int code stuff. If you're watching these videos in real time or whatever, I'll have more int code stuff for sure and other puzzles. But this is just to say I really appreciate everyone's comments and feedback. I'll keep doing the int code. If you have an online puzzle, though, or something that you'd be interested in me doing, send it my way. I'll add it to a list. I do have a list of things that are kind of interesting that I thought might be fun. And you will pepper those throughout the, besides just doing int code stuff. So with that, let's get started. So this is the puzzle that I saw, and you've probably seen this before. It's called the wall game. I presume it's just because you pass through the red and blue walls. But it's actually relatively simple. You're given a kind of a maze, and you're told you can't. The only rule is you can't pass through the same color twice. So the idea is you start here and you're going to end here, and you need to alternate colors, right? So you can't go red, red. You have to go red, blue, red, blue, red, blue, red, blue, red, blue, so on and so forth, right? That's the idea, is you just have to alternate, and can you start here and end here? So maybe I can just talk briefly about the way that I was solving it in my mind when I saw it. And again, I think I've seen this a couple times. Like most of the internet, things come up again every year or two, and people find it novel and new, but it's probably been around longer than you realize. I'm pretty sure I've seen this before, but it came up again somehow, and I saw it, and I solved it. The thing that got to me, was, is there a way for me to solve it programmatically, and would that be fun? So that's what we're going to talk about today. Is there like a fun way to solve this programmatically? And I had fun solving it. So hopefully you guys will have fun watching me solve it programmatically. But let's just think about like how I solved it in my head, to because I think that kind of helps get in the mindset of how you might try and solve it programmatically. Oftentimes, if you do something on pen and paper, or just thinking it through, talking about it, that can inform you on how to solve it programmatically. So that's what we're going to do right now. And for me, the thing that was going through my mind was trying to solve it in reverse. There's definitely ways for you to cycle, right? So you can go blue, red, blue, red, blue, red. Like these are cycles right here. You could cycle forever. I think you can cycle right here forever. But the thing that as I was looking at the puzzle that was interesting to me was I have to exit blue, which means in this room, I have to enter this room right here, this L-shaped room, in from a red one. And if I go through this red one, so if I come through this red one to here to get to the end, the actual only way that I can get to this room from a blue is to come back in this L room, right? So this is not a good, we know this would not be a good solution because this is just a loop, right? So we know that's not the solution. So it must be this red line is how we get there, right? So if we go blue, red, then the question is, what blue should I go to? Well, this is the only blue. If this blue would get me back to the L the room that I just left. So that's no good. So I probably have to come from this room right here, right? This is the only other way. So then again, because I came blue, the only one I can leave is red. So now I'm stuck in this red room. Interestingly enough, this whole room is all red. except for blue right here. So I'm in here. I've been through a red. Now I know I have to switch back through. So now I'm back to needing to exit a red. And from there, the solution became somewhat trivial because I know I can go red, blue, red, right? So I did it that's how I solved it initially. I did it in reverse. But once you kind of start thinking through the patterns, you say to yourself, oh, there's some tricks to this, right? Obviously, I don't want to like go through a loop. I don't want to loop forever. And additionally, I need to track some kind of state, right? I need to know that the previous door that I've gone through. And once you can do that, the problem becomes relatively easy because you can you can kind of say to yourself, oh, I if I've been in this room and I've entered it through a red door, there's no reason for me to try that, right? Like if I've come through this way and done some work, and somehow I go around this way, and I come back in here, I know that that's not actually helpful because I've already entered this room through a red wall, and so there's no reason for me to enter through a red wall again, if that makes sense. And that was the thing that was going through my mind as I was solving this, is it started eliminating possibilities and made like the solution somewhat trivial because there's only so much you could do, right? You can really only go here to here to here, back through, then here to here to here to here to out, right? So that's how I ended up solving it in my head. It did take a little bit of time for me to figure it out, but once I solved it, I started thinking about like, oh, I wonder if there's a way to programmatically solve this, right? And that's what excited me about it. Is like, ooh, can I write a program that would solve this? And, everyone's first solution is probably to say, oh, is there just some kind of brute force approach that I could take to solve this problem? And I think you probably could in this case. There are some gotchas, namely that this little loop here puts you in the same room. So you kind of have to do some like watching for loops and watching for backtracking. Like you don't want to like just loop forever in your like brute force approach. So you kind of want to say like, oh, if I visited this node before from a previous color, I don't want to visit it again. And you could probably traverse, through the maze to solve it. With just a straight brute force approach. Like, can I just try every way? And why is that? Well, the number of ways that you can choose from any given room is relatively small, right? Like if you're in here and you've entered here through a blue door, there's really only 2 places you can go, right? And so you just need to know, have I gone into that room? Have I gone into either of these places? Otherwise, I'm going to try the 2 places and give it a shot. And again, there is some difficulty in that because you do need to track colors as well, right? So if you're thinking about a brute force approach where maybe you're doing recursion, you need to know where you've come from previously, and you need to know like the whole path you've taken previously, because if you ever get stuck, like let's say again, like a loop like this where you go red, blue, red, blue, red, blue, you need to know like, oh, I've already entered this room from a blue one before, so it's not worth me trying that again. Someone else has clearly already done that and got me there, so I'll just keep doing that. As I started thinking about the brute force solution, though, the thing that came to my mind was like, well, how will I represent this problem in a data structure? Like, what's the data structure that I would use? And my mind went to graph. And so that's why, in the image, it's always a graph, right? I don't know. Sometimes, why is that? Sometimes it's really easy to reason about problem solving with puzzles and even in game mechanics and things like that with a graph. And if you can treat it as a graph, there's efficient solutions for it. You don't have to just brute force it anymore, right? That's the thing about it. And so, yeah, when I was looking at this, I was like, oh, you can kind of treat the walls as a nodes, and then the edges as or sorry, the rooms as nodes and the walls as like the edges, right? And you just color the edges. So instead of giving each edge like a cost, a number, you give it a color, and then you just track the previous color you've been on, and you can kind of go through it, right? Well, I'll show you more about that in a second. But again, I just want to say, like, some people will be like, oh, another graph problem. But the reality is again, when you know, when you look at a problem and say, oh, I can represent this as a graph, suddenly you have like the totality uh, of the knowledge of a bunch of smarter people than you who have learned how to efficiently solve graphs before, right? To answer these questions. So once you treat this as a graph, it's just as simple as, can I fit this graph into a good algorithm? And the algorithm that I picked that I'll show you the results for is Dijkstra's. We've talked about it before. I won't go into too many details of Dijkstra. I have previous videos on that. There's lots of good information. There's wiki pages that describe it. Obviously, though, if you have questions about it, if you've gone and read or watched previous videos and you have questions, feel free to ask in the comments. I'm happy to try and do it. But again, the puzzle was small enough, and there's really only the question of what's the previous door I've entered. So something like Dijkstra's seemed like a perfectly good solution for me. And that's why I went through it. So given that, what does this look like then, this wall game? What does it look like if we draw it as a graph? Well, I turned it like this. I made a graph like this, and you can kind of see if I create I kind of tried to create the graph, I guess I should say, to look a little bit like the way the rooms are oriented. So here's the start and here's the end. I labeled it T because E, I already labeled this. I don't know why I did that. Anyway, so here's the start, here's the end, and your goal is to traverse the graph. The one rule is you can only traverse the graph. You can only traverse an edge if the previous edge you traversed is the opposite color, right? And so thinking about this in this way kind of makes the process fairly trivial, right? Like if you're thinking about it this way, if you go from S to A, the only places you can go are E and B, right? And so you can start, again, even the naive brute force approach is just, okay, well, I've got two potential neighbors. What if I try both those neighbors? And then you can do the same thing from B, right? From B, you've gone blue, so the only place you can go is C. And notice here again, C has all these red nodes. The only way you can go out of C is to actually traverse through C again, and then you can go back out to B, to A, to E, and to T, right, to solve the problem. And this is where I think the gotchas come in here, right here in T or in C. This is like the gotcha for many of the naive approaches, and I actually think this would be a fun like programming puzzle problem to give to like people to try and solve, for interviews or whatever, because this little C can cause problems, right? If you are doing like the brute force style or like a recursive approach to try and solve it, or even doing a depth first search approach, those type of things, you need to be cognizant of this C needing to go back to C. So if you're doing something naive of like, oh, my visited nodes are just the node name, that's not going to work. What you need is the node name and the previous color, because it's okay to go back to C if you're traversing it over a new color, right? Going from B to C to D is okay as long as you haven't like gone that way, because how do I say this? Going from B to C to B is okay because you're entering C from a new color, right? You're not entering it from red, you're now entering it from blue, and that allows you to go back to B, which is okay. And the reason you can go back to B is because when you first entered B, you entered it from a blue color, so it's okay to go back up to B. And now when you enter it again, coming back this way, it's okay to go back this way because you're entering it from a red, right? And the same thing with A. So we'll show it one more time, right? I go from the first time I go to A, it's with a red, right? So it's right here. I'm entering it via red. When I'm going back to the solution, I'm now entering it with a blue. So it's okay to go back there, right? So I've changed the state is the way to think about it. And that's the thing with like Dijkstra's algorithm, right? Is what you're really interested in Dijkstra is like a few things, right? So the underlying implementation has some needs. It needs to know, what is my end game? How do I know I'm done? And it also needs to know, like, what are my neighbors, right? So given any node, what are my potential neighbors? And we might treat them as specifically a node, but in this case, we actually want to do it via some kind of state, right? I don't think I called it state in the code because it overlapped with just like the edge thing. But in this case, we say, okay, the neighbors that I want, the neighbors of any given function or any given node are any edges that are like the opposite color of how I entered it. So if I come into B from A, I've traversed a blue edge. And so I know I can't traverse a blue edge again. I have to go to C. So when I ask the question, what is the neighbor of B from a blue edge? The only answer to that should be C, right? So my neighbors, I need to track this state. I need to know the node, but I also need to know the color, right? What is the color of the previous node I visited? Or sorry, the previous edge I used to visit that node is the way to think about it. So this is all, and this is where like the difficulty comes in, right? Like of solving a Dijkstra's algorithm. Again, I'm not going to like go over Dijkstra's too much, but these are really the two things you need to know, right? Is like, what are my neighbors and what is my end state? Because once you do that, Dijkstra's will do all of the other work, right? It will keep track of the visited nodes, and the frontier, and it will like pick which nodes on the frontier to pop off and try and traverse, and it will look at the visited nodes and not visit them again if they've already been visited. But in our case, remember, it should be okay for us to visit nodes, so we have to like I don't know, we have to call it visited-ish, I guess, something along those lines. We want it to visit it again. We just want to visit it only if the color is different from how we got there before. And maybe a good way to think about how this, I was trying to think about like how to describe this is, what we've actually done is we've taken, and you do this work when you're doing finite automatons in computer science. You'll take like states like this, and break them up, right? Really, what we're saying is C is actually how do I describe this? C is actually two nodes, and what are the two nodes? Well, let's call one like C C1 and one C2, and the link between them, these aren't going to be the same colors. The link between them is blue, and then the link between B and C and D, and these are all the same. But we also want to create links to this one, right? So we'll create links this way. Sorry, this is getting a little ugly, but this is essentially what we're doing by creating this like kind of neighbors class thing right here, right? Right here, this part right here, by creating a set of neighbors where their state is both the node and the color, it allows us to visit the C node multiple times. And what that has the effect of doing is kind of exploding the graph in this way, where C is actually shown twice, connected by a blue node, and then we link all these nodes together. But now we can do proper traversal, right? So we know we can go from here to here to here and back to here, but we would never go from here to here to here to back to here again, because we know we've done that before. And we would also never go like from here to here to here to here to here, because this is already this C1 has already been visited by a red path via this way, right? So we just wouldn't visit that node again. And that's what this neighbors thing using multiple values for the state kind of does. And again, you kind of do this stuff with finite state machines and stuff like that. When you're building these state machines, you find these little places where you can simplify it like this, and it allows you to traverse the graph easier. We don't need to do any of that, but if you're familiar with that stuff, that's kind of what we're doing here with this thing, and I thought that might help it. And why do I bring this all up? Is I think when you're looking at when you're trying to solve this graph problem, you may run into like some issues that you don't really recognize until you like think about the graph as an exploded version of it. When you think about the graph exploded this way, or using this kind of like state and neighbors issue, or state and neighbors solution, I should say. You're saying to yourself, oh, how do I solve this? Because I want the ability to go back to C. Like if you were implementing Dijkstra's yourself, you'd say, oh, I want the ability to like go back to C, but only if I've seen red before. And you may start thinking like, oh, do I need to like track my path and check for loops? Or do I need to, does my visited node need to be like a 2D array? I mean, that would potentially work. You'd have like instead of just like a list of visited nodes, you'd have like a list of red visited nodes and blue visited nodes, or some kind of 2D array that was tracking like which ones you visited and which color, and decide whether it's okay to keep traversing that and those type of things. Again, Dijkstra is a path finding with distance. Usually we aren't using distance here, so you'd actually, it's trying to find the shortest path, right? And so it's still going to solve this problem, but I hope what I'm trying to get across is you can really confuse yourself with graphs if you don't like think about Dijkstra's algorithm or similar algorithms as like these two high level things. What is my end state, and how do I find my neighbors? And then as a sub part of like how do I find my neighbors is, it's not always just what is the adjacent nodes. And we've solved this way before with other Adventa codes, right? In fact, if you remember, there were a couple puzzles where you had to like walk 4 spaces and you couldn't walk. Let's see, it was something along the lines of you had to walk at least 4 places in the same direction, but not more than 10. There were kind of things like that where you'd have to kind of massage the state of Dijkstra's algorithm to solve it, to find the solution. And that's exactly what we're doing here, right? Is we're saying, hey, our neighbors actually has some constraints. We can't always go to C from B, depending on, well, that's not a good example. We can't always go from like, C to D unless we've, gone through C back again, those type of things, right? And so I hope I'm explaining this okay, and I hope that's coming across clear. Again, at a high level, the steps are, can I turn it into a graph, right? And that's not always the case. There's other solutions, right? There's always other ways to solve problems. We just happen to see a lot of them in puzzle solving. And I think the nature of it is because a lot of puzzle solving is, they tend to look like graphs, or you can kind of mold them to fit as a graph, right? But once you know it's a graph and it's kind of a path finding or a shortest path type thing, you can use something like Dijkstra's. And then just ask yourself the question, if I can use Dijkstra's, all I need to know is, how do I get to the end? How do I get to the end? And what are my neighbors? And once you've figured that out, maybe you have to use some special state that will help you solve the problem, right? And So all of that last 10 minutes or whatever was to hope to get you to understand that that's where you can go. So please keep that in mind, right? Is it a graph? Can I solve it in Dijkstra? And if it is, then does it have an end node? How do I figure out if I'm done? What's the end? And how do I create my neighbors? And so that's actually what the solution looks like. Let's just go to it right now. We could talk about this in a minute. This is actually how I showed it. Maybe we'll take a short detour, and like the question is like, how do I describe a graph? And this is, it turns out, how I described it. It's kind of silly. You could do it some other way. Basically, I said from any position, how do I get there? I give it a color and a label to where I can go, and that's how I'm going to import it. But let's actually not talk about that right now. I do want to talk about, I will go over all the code, but what I really want to go over is that part of the thing, right? I want to show you like how simple solving it with Dijkstra is, right? Again, I need to start somewhere, so I'm going to create a start. How do I know if I've succeeded, right? So here's my function that determines success. Given any edge, if the node to that edge is the end, then I know I've reached the solution, so I know I'm done. So the success is relatively easy, right? If we ever get to a node and it's the end node, we're done, right? So then the only hard part is, what are my successors or my neighbors, right? It's called successors in the pathfinding library that I used. So the pathfinding crate, we've used it before. It wants you to give it three things: the start node, the successors function, and the success function, which is this right here, right? So then all we really need to do is, how do we determine the successors of a given edge? And I'll show you the data structures in a second. And it's really just, we look at the graph, right? Not there, right here. We look at the graph and we say, I'm going to iterate over all the edges of the graph, but I'm only going to include values who have an opposite color or no color, right? The no color is just start at the beginning. I have no color, and that's why that's there. But otherwise, it's just, I say, hey, if it's the opposite color, then I know that's a potential edge, and I just I just keep track of all those ones that are successful and return that as my successor function. So we can I'll describe this a little bit more, but again, I just want to show you how powerful this can be. This solution may initially feel relatively complex, but once you've gotten to the point where you've said, oh, I can treat this as a graph, I lost my notes and stuff here. Once you say, oh, I can treat it as a graph, and once you know it's like a find the path, a shortest path type thing, you know you can use something like Dijkstra's. Again, you could use other pathfinding algorithms. There's a bunch out there. Dijkstra's was easy enough because we're just really picking between two colors. So like the state mechanic that you're holding is really small, and that's what you used. But this is all the code, right? There's really not much to it, and you've now solved a very complex problem. And I'll say, excuse me, not only have you solved a complex problem, but you've solved it in one of the more efficient ways you could solve it, right? This thing could potentially be infinitely big, and we know that Dijkstra is a relatively efficient solution to that problem, right? It's not going, the brute force solution would become extremely hard as the size of the nodes the number of nodes and the number of edges connected to the nodes increased. That it would become quickly unsolvable the higher those two values got, right? But because we know we have Dijkstra's algorithm to the rescue, we know that we have an efficient solution to solve it. We don't have to go through all the rigmarole of trying to solve it in a more complicated way. And I hope that's one thing that you get out of some of these solutions is, oftentimes the solution can be quite well self-contained and quite small. You just need to be aware of the algorithm. So it's okay to do some Google searching and saying, hey, what's an efficient algorithm for pathfinding and stuff like that, right? We've talked about that, all that stuff before. I just, again, this is what makes part of this puzzle solving makes it cool, is that you can take such a little bit of code and solve a huge problem. Okay, so given that, let's dig into like the rest of the code, because there's a bunch more here, right? Let's dig into it a little bit more. Obviously, I we need to track the colors, so I have a color enumeration here: red, blue, and none. None being like we're at the start, so we haven't like traversed one yet. You could potentially have, if you know what your original color, what your first node's color exit is, you could potentially, like in this case, we knew we were always going to go from S to A. So you could technically start as blue. There's also the reason why I didn't do that is because in a I tried to make it somewhat generic, although I only used red or blue. But in other solutions, you may have multiple entries with different colors, and so you may want to have none so you can try all those different paths, right? Like imagine if B was the initial starting point, you'd want to try C and E and A and pick based on those, but they're different colors. So in that case, you want to um, you want to be able to try all three of those. I just chose none. Obviously, this doesn't work if you have multiple colors. Um, the at least the enum doesn't. You'd need to add multiple colors to the enum to solve it, so that might not always be great. You could potentially, instead of using an enum, just use like a string of the color. Again, and so I'll show you the way the graph is represented, but then you could potentially use any colors and any node names. But I just implement, a display and a from to make it easy to like show the colors. And then we want to know about an edge in a graph. And again, I didn't use a state. We talked about, the state here over on this side. I didn't call it state because it turns out the struct edge is the same as that. I guess I could have used like a type definition, but what do we need to know from each edge is like what is the color and what node does it go to? And that's let's see. You see here, like when I'm talking about when I'm like I create the graph, right, from this wall puzzle.txt. I want to be able to say, to get to A from S, you need to traverse it via a red. So you need to know both the color and the node that the edge is leading to, I guess is the way to say it. So that's why you have a color and a node for each edge. And I just have a little helper function here to create the edges. You'll see in a minute why I do that. I decided to use nom for this one. I didn't need to. It'd been a while since I used it, and so I thought, it might be fun to do this. I think when I was typing it out initially and just trying to see if I can solve it, the AI created a bunch of like parse unwraps that did it for me, and that was fine. But I wanted to use nom. So what does that look like? Well, I can use the from string, or I can use nom in from string. I just had to do a little magic, and I think I found this online somewhere where I parse it, and then if it's okay, I return the puzzle. Otherwise, I return this error, and that allows me to do a from string. So I can easily turn, you'll see in the code later when I'm doing testing, I can easily turn this into a puzzle just using the parse function and stuff like that. The from string helps me do that. So how does that look in nom? Well, I guess I show these again. There's kind of like again, I think the easiest way to think about nom is to like think about at a high level what you want to do, and then like kind of do that recursively, go down and solve each piece on its own. So obviously I'm going to have multiple lines that are going to have the entry point, or sorry, the node, and then the edges to that node. So I'm going to have a separated list by new lines. So that's what I do here for the puzzle, parse the puzzle. I'm going to say, hey, for each new line, call this parse node function on the input. And, so split by new line and parse the node. If you're new to nom, I should say, by the way, feel free to go back and look at some of the previous videos where I used nom. In fact, I think I put nom in the title so you can see how that works. So what does this parse node look like? Well, now I've got a single line let's take this one, for example. I've got this single line. What do? I'm going to get a character, right? I did an alpha one. I'm going to get some string, and then I'm going to get a space, right, for here, right here. And then I'm going to get a space separated list. That's what this is doing right here, of each of the edges for it, right? So I'm going to get this part, and then this part, and then this part is the space separated space separated list of edges. And that allows me, and so based on that, I now have the node and the edges, and I can return that value to here in the parse node that allows me to collect my nodes, right? So what does this parse edge do? Well, I'm going to have this space separated list of each of these, but if I'm working on a single one, it's really just the colors, colon, and then the edge that I'm going to, right? So that's what this is right here. I just say, okay, give me a color, and then I should expect a colon, and then I should get the node name, and then I can do some conversion to turn those into the things. And that's what the nom parsing looks like. Again, it's probably overkill. I actually think the code is close to the same length. If I did this all in one thing, I'm using functions and commenting here to simplify it. But it's probably 6 of one, half dozen of another. If just doing parses and unwraps versus doing something like this. But I hadn't used nom in a while, so I thought it'd be fun to try it, and that's why I tried it. Again, it's not really complex. Nom, especially if you're worried about performance, really does a lot better if you're trying to do something along the lines of, can I parse a whole programming language where I have complex rules, and there's multiple ways to define a for block or things like that, right? That's where nom would probably be better for this case, but I thought, I should just try and remember how nom works so I can do it, right? So did I mention, I think I skipped over this, but the puzzle itself is really just a hash map that says, hey, here's the node and here's the edges to that node, right? Given this edge definition. So all of this turns into a structure that, it's just a hash map of here's the node and here's all the edges to that node, right? So you can kind of traverse the graph. And that's where, when we're calling the solve function, we use this right here, right? Is whenever it says, hey, give me all of the successors or all of the neighbors to a given edge. Again, this is somewhere that I've been before. I have a previous color and I have the node that I'm on. So I can say, hey, get me all the edges of that node. And then I can iterate over those edges and do a filter map. And just to kind of recall what filter map does, you either return something or nothing to a filter map, and it only keeps the ones that are something, right? So I'm going to iterate over all the edges, but I'm going to return none unless my previous color is none, or my previous color is the opposite of my current color, my current edge's color, right? And again, this has the effect of the alternating, right? I'm never going to consider a neighbor that I couldn't get to because I've been to that color before. So I do a filter map to get that. And then again, it's Dijkstra's. And so it wants a length for each of the edges. I just give it 1. They're all the same. The real logic here is doing this. There might be an easier way. Now I have to look at the pathfinding thing. I wonder if you can do Dijkstra's without edges or have a default of 1 edge. Anyway, that's my successor function. And then all I have to do is run Dijkstra's on that, right? I can say, here's my start, here's how I find my successors, and here's how I determine if I'm done. And yeah, I kind of do it in this like functional style way where I do a filter map and then another map, and then I collect all those to return my successors function. I also do this funky map here to return the actual solution. When you run Dijkstra, it actually will solve it all the way. So again, Dijkstra, how do I say this? It may not always be the best solution to run Dijkstras like this, but it worked just fine, I guess is the way to say it. Okay, so how do we run that? I also used clap to give it a, because I wanted to pass the file and the start and end nodes. That allowed me to like test other things. So I used clap to create a little parser. I don't think I've talked about clap before, but if it's something you're interested in, I could talk about that too. It's just a command line parser for you, and it allows you to create structures like this, and then it does the parsing of the command lines for you. So I need a file, I need a start and end node, and then I can just use the parse right here to get those values. And then it's as simple as, you give me a file, I'll parse it into a puzzle, and I'll try and solve it. And if I got a solution back, I know I can print that solution. Otherwise, I just say no solution is found. This main function is pretty simple, right? Parse the stuff, try and solve it. Otherwise, return no solution found. I did run this print solution function. Again, there's not much interesting with this either. The idea is I wanted to show kind of like going from node to node and what color I used. So I do this like little thing right here to show that. I did have to use clone from because I'm using sums here. So that might be something if you're using Rust and kind of new to Rust. My previous incur start at none when I'm looping through this state. And so I can do that. There might be other ways to do this, right? Like the previous could be the initial one and the cur could be the second one, and then you're just looping through. Like you skip the first one to loop through it, but this way was easy enough. And then I just have a bunch of tests. I won't go over the tests, but you can see like, I think one of these, this one is actually the solution to the wall puzzle. So we can, thanks, I think. You can see here I did a cargo test, all of it looks okay. And when I give it the actual wall puzzle, it solves it, right? And it shows you, you start at S and you go red to A, and then you go blue to B, red to C. And again, notice here you're going blue back to C, and then from C, red back to B. And just to reiterate, we can do that because we're tracking both color and node. And that allows us to retraverse those nodes to eventually get us back to the solution. And that helps us solve this problem. Okay, so that was a lot, but I hope it helps you get an idea of like how cool graphs can be. Again, Dijkstra is an easy one to throw out and to solve a problem like this. You could probably find some more interesting ways to solve it, but I just think one of the things that's really cool about computer science and learning about data structures and algorithms is that once you can fit it into those data structures, you now have algorithms at your disposal that really simplify the process. And that's what I think is really cool about all this is I can it took me a while to think about it, and I did some refactoring, right? So I don't want you to think that I just wrote these 30 lines of code after like 10 seconds of thinking about it and solved the problem. But I think it's really cool that you can go from, hey, how do I solve this problem to, literally like 1 to 15 lines of code, somewhere on that order, and you've solved the problem, right? I just think that's really cool, and I think that shows you the power of understanding graph theory and practicing on these puzzles. This is why I like doing these puzzles, is because this kind of practice will be useful to you with whatever you're doing in the future, right? Uh, if you're programming, whether it's on a front end or wherever, solving these puzzles really expands your mind, right? Don't just go for the brute force approach. Look for why this puzzle is there and how you might be able to solve it efficiently. And that will, like, you'll be able to add these things to your toolkit to solve problems, obviously more puzzles, but also in the real world, right? I think I've told stories like this before, but um, I think one of the biggest things that some people miss out on are not understanding these things. And so when I've said before to coworkers, oh, we can solve this with depth first search or breadth first search or something like that, right? And they don't know what that is, and so teaching it to them, it will blow their mind, right? Because in 10 lines of code, it doesn't look like you should be able to solve the problem, but because someone smarter than you has done all the work and the proofs and the verifications to show that it works, it feels like magic. I don't know. I don't know how else to describe it. Is when I'm solving these puzzles, it just feels like magic. So I hope it feels that way for you. I hope you had fun going through this with me. If you have other puzzles, I would love to try and solve them. Obviously, I will get back to the int code stuff. We'll keep doing that. I've worked on a couple of the next days. I like to polish, right? So again, like I said, this code I just didn't write it like this, and it came out like this in 10 minutes. I worked over this several times, reread it several times, just like you did an essay in high school or whatever. I did multiple drafts to get it to where it is. I have a couple of the int code ones solved, but I want to kind of go through it and polish them up and make it something that's worthy to show in the video. And so I think we'll keep doing that. But again, anything you want me to talk about, more puzzles or more stuff like that, I'm happy to do. So there you go. Have an amazing day, night, whatever, whenever you are, and happy coding.